All right, so yeah, William will continue torturing us with the pseudo-randomization for space-bounded computation.
Thanks.
After a wonderful lecture.
Thank you. Yeah, thanks for coming. Thanks for coming again. For those of you who were here yesterday, happy to be here. So yeah, my name is William, and today I'm presenting joint work with Lijia Chen, Xin Liu, Avishai Tal, and Hongxun Wu. And so this work is about weighted pseudorandom generators. Okay, and if you were here yesterday, then maybe you have some idea of what that means. But for those of you who maybe weren't here, or for those of you who need a review, let me explain. So let's let F be a class of functions that we're interested in fooling. Mapping n bits to 1 bit. Then the traditional definition of a pseudorandom generator would say an epsilon pseudorandom generator for F is a function stretching some short, truly random seed out to a long pseudorandom string, such that for every function in this class, the acceptance probability of this function is the same to within plus or minus epsilon, whether you plug in n uniform random bits or you plug in n pseudorandom bits that you get from the generator. Okay, good. The twist now with this weighted pseudorandom generator is that in addition to this function g, we're also going to have a weight function that assigns real valued weights to each seed of the generator. Okay, so we call it a WPRG. So we have G and also rho, where G still maps an S-bit seed out to an N-bit string, and rho is mapping the seeds to the real numbers, such that for every F in our class, the expectation of F on a uniform random input is well approximated by this experiment where we pick a seed at random and we stretch it out and plug it into F, and then we multiply by the weight of that seed. Okay, and as I suggested yesterday, these weights, the key thing about these weights is that they are permitted to be negative, okay, which means that this expectation where we multiply by these positive and negative weights, it's almost like some kind of expectation over a probability distribution with negative probabilities. Okay, yeah.
So I guess we could like assume that the weights are like +1 - 1, is it actually?
Not +1 - 1. In all the constructions we know, they do all have the same magnitude. It's just a matter of sign, but the magnitude is like a small number, not plus or minus 1. So it's like plus or minus delta for some small delta. Yeah, so you can verify that this definition implies that these weights satisfy a bunch of properties. Like, for example, the average value of rho, this weight function, has to be 1. If our class F is like anything non-trivial, because this definition says that every function is fooled. So in particular, we should fool the constant 1 function, right? And the constant 1 function has expectation 1, which means that the expectation of the weight function should be plus or minus, 1 plus or minus epsilon. So you can verify, that this definition sort of immediately implies that rho can't be too wild. But the important thing is that it's allowed to be negative. That's really the key. Yeah.
I think I missed something. The expectation should be 1, but then you can assume it's plus or minus some small delta.
But not equal. Doesn't
Sorry?
have to be equal number of pluses or minus. Expectation can still be 1.
Oh, okay.
Right. Yeah, that's exactly. Good. Okay, good. So, okay. So comparing these two, okay. When we're trying to construct these generators, the fact that we're allowing negative weights works in our favor, right? It makes our lives easier. It gives us this extra flexibility. It makes it so that potentially we can achieve a shorter seed length. Okay. And indeed, that is how the state of the art currently is. So we're going to be particularly interested in fooling functions that are defined by this model of standard order read once branching programs. Okay, so let me quickly review that.
I will understand your question. Yeah, if all the weights are bounded by 1/10, the expectation in absolute value of the expectation will never be 1. Some of
This is a
them
good
have to be
point.
larger.
This is a good point. I think I'm getting mixed up between. So there's an issue where there's this weight function where we're taking an expectation, but you could also do the definition where we're taking a sum instead of the expectation, right? And they differ by a factor of 2 to the s, and I struggle to keep them straight in my mind. So I think here I should be saying it's plus or minus some delta times 2 to the s. So the important thing is, to answer your question, is that they do all have. It is a matter of sign. They're going to end up having the same magnitude in the constructions. But yeah, you're absolutely right. Thank you. This time the magnitude is going to be large. It's larger than 1 actually. Yeah. Okay. Yeah. Good. Thank you. Yeah, the original paper that defined these. This notion is due to Braverman, Cohen, and Gard. And originally they were thinking in terms of a sum. You write a sum here instead of an expectation. It's turned out that this definition is probably the better one to be thinking about this, so I ought to get it straight and internalize it better. This is probably the more useful way of thinking. Okay, good. Okay, so yeah, the functions that we would like to fool are the certain type of branching program.
So just because I was on Zoom and I dropped like yesterday. So this basically saying if you have this, you can still de-randomize, you can still run over all the seeds, right?
Good. Yeah. So when we're trying to, like I was saying, when we're constructing these, the weights work in our favor. If we're trying to use these things, then okay, the weights potentially work against us. But if we have like an optimal explicit construction, the weights are still okay if we're trying to de-randomize algorithms, right? We can still afford to try all possible seeds, and we can compute this expectation if we have like an explicit weighted pseudorandom generator with a very short seed length.
But then you could also just look at any function of x and f of g of x, right, or something, right?
Yeah.
It doesn't have to be multiplying by a function of x.
Oh, yeah, I follow you. Yeah, that's right. Yeah, so you could consider a more general definition. There's a concept called a deterministic sampler, which is a more general definition where, we're an oracle algorithm. You make queries to f and you do whatever you want with the responses to those queries. You could combine them by taking a linear combination like this, or you could combine them by, doing some more complicated Boolean logic. I mean, you could take medians, you could be adaptive. Yeah, so you can generalize this definition further. This isn't like the most general possible thing, but this the structure here has turned out to be useful. So for example, yesterday I was telling you about the current state-of-the-art de-randomization of space-bounded computation, which uses weighted pseudorandom generators, and it actually does use this this nice linear combination structure. So it's like, this is some kind of like Goldilocks concept where we're trying to introduce just enough flexibility into the definition to facilitate constructions, while retaining enough structure of the original definition that it still facilitates applications. Good. Okay, good. And so yeah, we were just talking about de-randomizing space-bounded computation, and if that's your goal, then the functions that you want to fool are these branching programs. Okay, so width W, length N. We're always today going to be thinking about the standard order case. Standard order read once branching program. I'll just draw a quick picture. So it's a branching program where the vertices are arranged in layers. Each vertex has two outgoing edges pointing to the next layer labeled 0 and 1. And the interpretation is that in this first step, we read a bit x1 to decide which outgoing edge to traverse from some start vertex. And then in the next step, we read the next bit x2, etc. And then in the final step, we read xn. And these vertices are either accepting or rejecting. And the number of vertices per layer is the width. Okay, so this program, it computes some Boolean function f that takes these n bits, x1 up to xn, and then it outputs 0 or 1 depending on whether we reach an accepting vertex or a rejecting vertex. Good. Good. So as I just started to say, from the definitions, potentially we could get better constructions of weighted pseudorandom generators, and indeed that is the current state of the art. Okay, so if we're thinking about polynomial width read once branching programs, Nissan's PRG, a true unweighted pseudorandom generator, rules width W, length and standard order read once branching programs. Seed length log Wn over epsilon times log n. And a theorem from a few years ago by Braverman, Cohen, and Gard that there exists an explicit weighted pseudorandom generator for the same model. And the seed length is, well, we still have this log Wn times log n, but the dependence on epsilon is better. Okay, instead of log 1 over epsilon times log n, we just have log 1 over epsilon.
So how should we think about epsilon? Is it like 1 over n, exponent of it, like what?
Yeah, so for this theorem is most interesting, I think, if you think of epsilon as like inverse quasi-polynomial. Okay, so in Nissan's seed length, you don't start feeling the dependence on epsilon until epsilon is negligibly small, smaller than 1 over n. Here you don't start feeling the dependence on epsilon until it's like below 2 to the minus log squared n. Okay. Very good. Good. Okay, good. So that's sort of the status for the general case of read once branching programs. This work that I'm presenting to you today is about more restricted classes of read once branching programs that I hope you'll agree are still well motivated. Okay, so there are several different classes that we look at in the paper, but today in the talk, I'm going to talk about just two of these classes. The first is very narrow read once branching programs. Okay, so one way to try to make progress on this problem of fooling read once branching programs is to start with constant space programs. Okay, so the state of the art here is that for width 2 programs, we have optimal pseudorandom generators. Okay, But for width 3 programs, that's kind of like the frontier of current knowledge, where we can do some stuff, but we don't have optimal constructions. Okay, so for width 3 programs, so there's a theorem by Gopelin, Meka, Reingold, Trevisan, and Badon. They gave what's called a hitting set generator with near optimal seed length. Okay, a hitting set generator is like a kind of a one-sided version of a pseudorandom generator. It's implied by this definition of a weighted pseudorandom generator. So it's like it has less structure. They're even easier to construct, but they're also less useful.
For width 2, it's just an epsilon bias set.
No, actually. So an epsilon bias set, it does not do a good job for width 3 programs.
Width 2.
With two.
For width 2, oh yes.
Width 2 is just epsilon bias.
That's correct. That's correct. Yeah, yeah. Yeah, for width 3, you have to do something more than. Yeah. Okay, so this was like about a decade ago. And then just a few years ago, Meka, Reingold, Tal gave a pseudorandom generator for this same model. With seed length, still this nice like logn, but now it's times log1 over epsilon instead of plus. Okay, so good dependence on n, but a not so great dependence on epsilon. Okay, so our contribution is a weighted pseudorandom generator. And I wish I could tell you it's optimal, but it's instead it's somehow intermediate between these two. Okay, the seed length is log n times square root log1 over epsilon plus log1 over epsilon. Okay, so for this work, you should think of epsilon as maybe 1 over n. Okay, that's maybe where this is most interesting. Okay, I mean, I think intuitively, like trying to understand the low error case, maybe it's not immediately obvious why. I mean, ultimately, maybe the moderate error case is what we care about the most, but this low error case is often important as sort of like intermediate steps for trying to, make progress on maybe more difficult problems. So that's kind of the.
You say that for width 2, you have optimal PRGs?
Yeah. Yeah, so for width 2, we can get seed length O of log n over epsilon, which is optimal.
Is there any sense that you say something about the final probabilities of getting the vertices, the 3 ending vertices? Can you say something about how bad can they be, or can they be any 3 numbers almost, or?
They can be pretty severe. So you can think, for example, a width 3 program could compute a read once CNF. And so this read once CNF could be doing something like the tribes function. It could be nice and balanced. Or it could be doing something, where like an and of very narrow ors, right? So the acceptance probability could be very, very small.
There's nothing intelligent you can say about like what could be there.
They can be very small. They can be moderate. Yeah, I don't know anything too profound to say. Yeah, so these width 3 programs, they can do kind of a lot of interesting stuff actually, even though they only have less than 2 bits of memory. They're already sort of formidable. Yeah.
Is there some belief that if you could do like, with the 100, you could solve the whole problem, or is there?
No, I don't think so. I mean, I think so. Realistically, I would expect, right, that if you can do width 100, you can probably handle any constant width. Probably we're not going to have techniques that are tailored to programs of width at most 100. And I think fooling constant width for branching programs, that to me is like a very appealing goal in its own right, because it's some sense of de-randomizing constant space computation. It's not, you shouldn't be thinking in terms of like Turing machines and Turing machines that use constant space or something like that. That's a sort of a different model, but I think it's an appealing notion of like constant space randomized computation. But no, we don't know like a reduction. Okay, good. Okay, the other class that we're going to talk about today is regular branching programs. So it's regular if each vertex has two incoming edges. Except of course, those in the first layer. Have zero incoming edges. Okay. And if you were here yesterday, I tried to motivate studying this class of branching programs. And so for some of those reasons, there's been quite a lot of work on this model. And what's most relevant to us, about a decade ago, Braverman, Rao, Raz, and Yehudayoff gave a pseudorandom generator with seed length log W over epsilon times log N. Okay, so this is most interesting if we think of the width as being very small, maybe constant. Okay, think about constant width programs still. We have this nice dependence on N, it's only log N instead of log squared N. Okay, but the dependence on epsilon is not ideal. Okay, more recently, just like last year, in joint work with Bogdanov, we constructed a hitting set generator for this model. Where the seed length is like, we still have this log W log N, but we improved the dependence on epsilon. Instead of log N times log epsilon, it's log N times square root log 1 over epsilon. Okay, so again, you should think of the width as a constant and epsilon as maybe 1 over N. Okay, the new result in this work is a weighted pseudorandom generator with the same seed length. So we're upgrading this hitting set generator into a weighted pseudorandom generator.
Is there a way to take on any hitting set and make it into a weighted?
That's a good question. We don't know any way to do that, and I wouldn't expect there to be one. If you can pull that off, that might have some consequences. Actually, I'm not sure. But no, I mean, I wouldn't expect to be able to do that, right? A hitting set generator is kind of like a meager thing where, I mean, we only know that there's like one good seed, right? A hitting set generator might usually output garbage. Right, that's very possible, and so it seems pretty difficult in general to just like sort of generically convert it, but I'm not sure.
At least like not generically. There's all these works where we compare hitting set generators to PRGs or weighted PRGs. So like, at least in these works, are the weighted PRGs somehow connected to the hitting set generators that were prior?
Yeah, there are connections sometimes. Yeah. Yeah, so in particular, I'm going to be telling you about an error reduction procedure that converts like moderate error pseudorandom generators into low error weighted pseudorandom generators. And some of these hitting set generators, like this one in particular, also come from error reduction procedures, but there we have sort of more tools available to us if we're merely aiming for a hitting set generator, but it's still an error reduction procedure, which is related. So yeah. Okay, good. So hopefully the statements of the theorems are clear. Great. I also want to quickly mention, so our proofs of these that I'm going to show you some proofs. I'll probably show you this proof in a pretty good amount of detail. That's my hope. They use like Laplacian methods, like we were talking about yesterday. And actually, very recently, subsequent to our work, there was a paper by Chattopadhyay and Liao, and they actually give alternative analyses of our same constructions. And their analyses, somehow they avoid ever using the word Laplacian. They avoid ever thinking in terms of Laplacian matrices. And so somehow it's like secretly equivalent. It's the same construction, but it's a different perspective. And so I think that's very interesting. I'm going to present the our original proof based on this Laplacian perspective, but I think probably both perspectives have value. So I encourage you to check out their paper if you're curious. Okay, good. So let's start doing the proof. I'm actually going to show you first a proof of this theorem, this theorem by Braverman, Cohen, and Garg. Okay. I hope you won't mind that I'm showing you a proof of a theorem that's several years old. For one thing, it's arguably more important than the new theorems, but also it's we're building on a proof of that theorem very much. So I think it'll help to set it up. Go over here actually and use this one. Okay. So there are several known proofs at this point of this theorem by Braverman, Cohen, and Garg. And I'm going to show you a particular proof due to Cohen, Renard, Sperlo, Dean, Cohen, Ron, Renard, Sperlo, and Tashma, and independently another paper by Pine and Badon also gave this same proof. So, okay, let's let F be the branching program that we're trying to fool. Okay. And let W sub I be the transition matrix for layer I. Okay, so this says the probabilities of going from layer I minus 1 to layer I. Okay. And then let's let W J from I be the product, WJ minus 1, W I plus 1. Okay, so we're using this notation because of the multiplication order. I guess I didn't say explicitly, but let's set this up so that we're using column vectors and left multiplication by matrices. Okay, so then this matrix WJ from I, this is the probabilities of going from layer I to layer J. Probabilities of going from any particular vertex in layer I to any particular vertex in layer J when you take a random walk of the appropriate length. Okay. So our goal with this weighted pseudorandom generator is we want to approximate the probabilities of going to the final vertex, final layer from the initial layer. So it's going to be, like I said, an error reduction procedure. Okay, so the first step is to use Nissan's pseudorandom generator to get a moderate error approximation to this matrix. Okay, and in fact, to all of the submatrices, these WJ from I. So. Use Nissan pseudorandom generator. To construct approximation matrices W tilde J from I, such that let's say the one norm, the specific norm isn't too important here, but let's say the one norm of this matrix is at most some moderate error value tau. Okay, and in particular, we should take tau. Yeah, tau should be polynomial. Let's say 1 over n squared w. Okay. And okay, I should maybe, you know, I should say, like, ultimately we're trying to construct a weighted pseudorandom generator. We're trying to construct something black box. So we're not going to be literally, the algorithm isn't literally constructing these matrices, right? Really, these matrices happen in the analysis. But I'm going to kind of, you know, describe things in terms of the matrices, and hopefully I'll be able to convince you that it's possible to reverse engineer the weighted pseudorandom generator. Okay, now it turns out that to decrease the error, it's helpful to collect all of these W by W matrices into one big matrix. Okay, so now we're moving to let W be the random walk matrix of the entire program. So now capital N here is the total number of vertices. Okay. So W has all these matrices W1, W2 up to Wn on the, you know, just below the diagonal here. Okay, and as we were discussing yesterday, if you were here, what we really want to look at here is the Laplacian matrix. And the reason is that if we take the inverse of this Laplacian, the inverse of I minus W, this is like a geometric series. Right? It's the sum of the powers of W, which is basically, it's the matrix of all the answers that we're looking for. Okay, as the identity is on the diagonal. And then the matrix that we're really interested in is in the lower left corner. It's this block matrix. Good. Okay. So step 2, given this, you know, inverse Laplacian perspective where we're looking at these big matrices, step 2 is that we're going to collect all of our W tilde matrices into one big matrix. So let's call it L hat inverse. Okay. This is going to be our approximation, our initial approximation to the inverse Laplacian. And for this proof, we'll simply collect all these approximation matrices.
It's using this one.
Right. So W tilde is defined by using Nissan pseudorandom generator. You just count, you know, how many seeds And here we're going to collect all this together. So this is still right, still using Nissan. The reason that I'm writing it very explicitly in these two steps of first defining the W tildes and then defining the L hat is that for our proof for the regular case, we're still going to have these W tildes using a base pseudorandom generator, but actually this is the key step that we're going to modify, the step where we somehow collect those all into some big matrix. So for this first proof, though, we do sort of the most natural thing for this BCG theorem. We do the most natural thing. We collect all the W tildes. We just put a W tilde in place of the corresponding W. Okay, good. Now this L hat inverse, then naturally, this is some approximation to L inverse. Okay, and in particular, L hat inverse, it approximates it in terms of the one norm, which is the norm we were using over there. It's at most tau times, and this is crucial, times there's some factor of n blow up here. Okay. I mean, the exact penalty that you pay depends on the norm. With the one norm, it's going to be a factor of n blow up, because basically it's like a union bound or something, or a triangle inequality. Because we've collected each of these matrices, each matrix has some error tau, and now we have an n by n grid of them. So we should expect that we have to sum over all the rows or the columns. Okay, so there's some factor of n blow up in the error. And then actually the error that we really care about is after you multiply by the Laplacian. We care about L hat inverse L versus the identity. And there you pick up a tiny bit more error, but that's not so significant. Okay, it's like a constant factor in this case that we're thinking about the one norm.
Why is this we care about?
Yeah, so why is this the thing we care about? The reason it's the thing we care about is step 3. So I think the next step is going to show you why this is what we care about.
Or it's profit.
Yeah, that's right. That's or maybe 5. But yeah. Okay, yeah. So we've collected all of these approximation matrices, and for this BCG theorem, this factor of n loss is no big deal for us. It's fine. We're starting with an inverse polynomial tau. Now step 3 is kind of where the magic happens in some sense. This is where we do this error reduction. This is a Richardson iteration. So let E be the matrix of errors after multiplying by the Laplacian. Actually, I think I want to do it the other way. Identity minus L hat inverse L. And let A sub M be this sum of powers of E times our initial approximation. Up to some M. And then something magical happens where after you multiply by the Laplacian, then you get this telescoping sum. And so it comes out to the identity minus e to the m plus 1. E is the error matrix. Yeah, so we've taken our errors and we've raised our error matrix to some high power, which means that everything's getting smaller. We're decreasing the total amount of error. Okay. And in particular, this means AM times the Laplacian minus the identity. If we take the norm of this thing, it's the norm of e to the m plus 1. And it is important that we're using a submultiplicative norm here. So it wasn't a completely arbitrary matrix norm. That's the norm of e to the m plus 1. And this is why we cared about the error after multiplying by the Laplacian, because this is e right here, or or negative e or whatever. So this is n times tau to the power n plus 1.
This is a standard way to reduce error for numerical computations.
Right, exactly. This is coming from this world of like fast solvers for Laplacian systems of equations, where they're caring about time complexity and they don't care about randomness complexity. But then this sort of recent literature, this was brought to the space-bounded derandomization world by Ahmadinejad, Kellner, Murtaugh, Peoples, Sidford, and Vedant just a few years ago, and now we're realizing that this has all these applications in space-bounded derandomization, which is not where it was born. So yeah, it's pretty cool. I think it's a very cool trick. This Richardson iteration thing is very neat.
So if you can approximate the Laplacian, this is an automatic way to get better approximation.
Right, and actually this Richardson iteration is very generic. It's like if you can approximate the inverse to pretty much anything, any matrix, then you can improve that approximation to the inverse by doing this stuff. You can even think about Richardson iteration in terms of approximating the inverse to a number. Like if you're trying to compute, 1 over 157 or something. Richardson iteration actually makes sense even in that context of just like taking the reciprocal of a real number. So it's a very general trick. And yeah, so here we're able to get some mileage out of it in the space.
So you need to have the actual matrix and an approximation to the inverse.
Right.
Or you have to have the exact matrix.
Yeah.
And some approximation for the inverse.
Exactly. And in our setting, the Laplacian itself is not something that is difficult to compute, right? The Laplacian itself is the identity minus W, where W is something you could read off the branching program very easily if you had the description of the branching program. So the Laplacian itself you should think of as given. And then the approximation to the inverse, that's what we're getting from Nissan's pseudorandom generator. Good. Okay, and all right. This is after multiplying by the Laplacian, but really, ultimately what we care about is before multiplying by the Laplacian. But that only picks up some factor of like O of n outside the parentheses. Here it's like n times tau, n plus 1, maybe times some additional O of n. Okay, and we can force that to be epsilon by choosing m sufficiently small. Log 1 over epsilon over log n w. Yeah.
I just n tau, not n squared tau.
Yeah, so that's sort of, it depends on the choice of norm, right? But if we're using the 1 norm, then we only need to sum over either rows or columns. I can never keep track of which. We only need to sum in 1 dimension if we use the 1 norm. And so in terms of the branching program, we're considering the maximum overall start vertices of the sum over all final vertices of the error at that vertex. Okay, and so the fact that we're collecting everything into one big matrix means we have to sum over layers. So we pick up a factor of n, but we don't have to, we don't have to pay for every single block in the matrix. But if you use a different norm, you might pay a slightly different factor here. It's not worth it. Okay, good. Okay, so that's really the key, where the magic has happened, but there is still a little bit more effort required to get this theorem that we're proving. So step 4 is that we need to reverse engineer this in terms of weighted pseudorandom generator, right? We don't actually have access to these matrices. We can't literally do this matrix arithmetic. We need this matrix arithmetic to happen in the analysis rather than in the construction, right? And so I might be a little bit hand wavy in this part because I want you to trust that it can be done, but I'll give you a little bit so you can see see what's going on. Let G be the distribution sampled by Nissan's pseudorandom generator. Okay, and let G, let's say, from I to J, the J minus I bit prefix of this generator, the first J minus I bits. So these is like enough pseudorandom bits to estimate probabilities from the ith layer to the jth layer. Good. Okay, and we'd like to think of this probability distribution. We're going to think of it as like a linear combination of strings. Okay, it's a probability distribution over strings. So think of it as a sum of strings where each string has a probability attached to it. Okay, so this might be intuitive if you're coming from, if you've ever done like quantum computing, where we think of a pure state as being some linear combination of basis states, right? Okay, so if we think in those terms, then it's legal to do things like take differences of these probability distributions. Okay, if we're thinking of them as sums. Okay. So let E. This is going to correspond to this matrix E. These are, if you were here yesterday, these are like local consistency errors. Okay, E from layer I to layer J is the uniform distribution on one bit tensored with these pseudorandom bits from layers I plus 1 to J. And we take the difference, this distribution, one uniform bit followed by a bunch of pseudorandom bits versus just a bunch of pseudorandom bits. Okay, so this is, now we've got negative probabilities, right? This is a pseudo distribution.
With the prefix, it's not simply it's not a prefix, it's some middle chunk of the.
You can do it either way, actually. You could take the middle bit, like bits I through J, and in some ways that's more natural, but it works either way. Basically, you also have the same freedom over here when I was defining this W tilde, right? You use this Nissan pseudorandom generator to estimate the probabilities of going from one vertex to another, where those vertices go from layer I to layer J. You can use a prefix of the output, or you can use a middle portion, either way. So we just need to be consistent about how we define W tilde and how we define this distribution, as long as you make the same choice.
Not the same distribution.
Right. Yeah, they're not the same distribution, but they both will have the appropriate properties that we need. So yeah. Okay, let me actually.
Because both this chunk and this chunk has to full J minus I length
Right.
computation.
Right.
So, sorry, I'm not sure that I'm following, because I was like taking the definitions as is, but now we're sort of saying you can change them. But like here, when you're saying tensor one bit with GI plus 1 to J, and look at G I to J, this is not I'm not sure if like is the new bit the one that's supposed to, like in GI to J, you're like looking at like bits 1 up to J minus I, and here you're looking at like one uniform bit and bits 1 up to J minus I, but the way that like, am I supposed to understand that the uniform bit that you tensored is supposed to be instead of the last bit or instead of the first bit? Like
yeah, so this actually has to do with like choices that are somewhat arbitrary. So okay, here as written, this U1 is like it's instead of the first bit. So it's one truly random bit followed by a bunch of pseudo-random bits.
But like the distribution of the second bit in the left thing is the same like the distribution of the first bit in the thing that you're subtracting.
Yeah.
So does that make any difference, or?
No, it doesn't matter. Like Avi was suggesting, you could set it up so that the second bit here is similar to the second bit here.
Okay.
That would also work. We have freedom.
Okay.
It's just a quality of one pseudo-random bit given a bunch of others.
And so if if that's more natural to you, then feel free to modify this definition in your mind.
No, I don't need to modify it in my mind.
Okay.
I want to understand, the intuition behind why we're even looking at this
Yeah,
where previously I was thinking, okay, we're sort of trying to compare. Never mind, maybe
You just need
That's okay.
to define the weights eventually so that it will be consistent with the analysis over there.
exactly. Ultimately, our goal here is just to come up with something that's going to induce this arithmetic.
the reason that I seem maybe a bit unhappy is that I'm trying to like reverse engineer this to understand the intuition behind it. So you've done some calculation with matrices.
Right.
And you've said, I started with some PRG and now I'm doing some calculation with matrices, and in the matrix world, I know how to reduce the norm using Richardson's iterations.
Mhm.
And now I'm trying to sort of better understand, like, how can I interpret like this like reduced norm matrix as a PRG, and I'd be happier if I wouldn't just get the recipe. I would actually like understand what's going on under the hood. I'm not sure if like I'm being very precise in my request. So that's why I was trying to understand whether I should ask these things to fit or not, or like what is the property that I'm looking for here. Like
One thing you didn't say is that the new weighted PRG is going to have a longer seed. You're going to add log1 or epsilon bit side to near Nisman generate. So you are going to get another distribution or weighted quantum distribution, whatever you want to call it. Yeah, so you want to take the probability distribution that was used originally by Nisman generator, and you want to, I don't know, play with it and get a different distribution so that the behavior of the circuit with respect to the new one will just fit fit this analysis. I don't know how it will go. I mean, that's why where I understand it's going. And for this, it needs some definition, and hopefully we'll see.
So remember, is there a way to explain why the weights are useful for? Like a black box thing, like you have a bunch of things and one of them works, and you kind of weight them in the right way, or
The minus.
This minus sign right here is the reason that we need weights. Okay. In this Richardson iteration, the new approximation matrix, our new refined approximation matrix, has a bunch of minus signs built into it. Okay. And so now we're trying to construct a pseudorandom generator that induces this same approximation matrix. We want this A sub m. We want this to be the matrix of probabilities, actually pseudo probabilities, the matrix of probabilities that you would get if you used our weighted pseudorandom generator to estimate probabilities. Okay. And so if we want a pseudorandom generator that induces this thing, then we need these minus signs in there somewhere. And that's what's happening right here. This minus sign is the same as that minus sign.
it's enough to explain how to do A2.
Yeah, that's right.
Same idea.
Yeah, absolutely.
More terms.
Absolutely. Yep. Yeah, so taking M a bit larger means we're doing more aggressive error reduction, but qualitatively, it's, the construction is very similar. So, so I'm not sure that everything's going to be 100% satisfactory or persuading, but I'm hoping that you can at least get some intuitive sense that like there is a way to do this backwards, and I'm hoping that by at least writing some formulas, you can have something concrete to see like, okay, this is ultimately how it does turn out. But you'll have to trust me a little bit. So this E corresponds to that E, and then the Richardson iteration here, this A sub m, what that corresponds to, when you can reverse engineer it is we'll call this fancy X superscript M. It's the sum, and then you have to sum over all like breakpoints in the middle of this program. Okay, so oops, that should be. And then we do first the pseudorandom generator, and then we tensor that with a bunch of this E thing. So this pseudorandom generator followed by a bunch of E's, that corresponds to, with the matrix multiplication in the other way, that corresponds to the L hat inverse multiplied by a bunch of E's. And the fact that we're summing, we have to do a sum over a bunch of different breakpoints. This corresponds to like when you do matrix multiplication, right? Matrix multiplication, you sum over all indices, middle indices, right? And ultimately, right, we only care about one block of this A sub m. We only care about the block that corresponds to going from the start of the program to the end of the program. And so this summation is saying, like, what is that block in terms of all the other blocks? So that's why we have this summation over breakpoints. But this is like a pseudo distribution, which you can also think of as a weighted pseudorandom generator. And the claim is that for our, if you look at like the pseudo expectation of our branching program under this pseudo distribution, what you get is exactly the bottom left block of this matrix A sub m.
So is it correct to say that there is like a translation between the operations that you do matrix-wise to operations that you do to distributions? Only like positivity plays no role there, so you're going to get so you're going to get like negative weights eventually.
Yeah. So everything, our matrix arithmetic translates into arithmetic in this strange space of pseudo distributions.
Mm-hmm.
And the minus signs over here, they just show up over there too. They're just still minus signs over there. And that's why we wind up with these negative probabilities. It's because we used minus signs over here, so we get minus signs over there too.
The intuition of the matrix multiplication here is not clear to me. Matrix multiplication, you fix a place in the middle. You fix it. You don't go over all midpoints. You multiply matrices by, right? You pick a midpoint, multiply the left chunk and the right chunk.
But we sum. Okay, right. So if we do, A times B ij, that's like the sum over K, A I K B K J, right? And here we're doing this is like e to the I, so we're taking some large power, right? So we sum over we have a bunch of indices that we're summing over, and that's this I0 up to IL. We sum over all I0 up to IL. And then for it to be non-zero, they have to be increasing because this is like a directed layered graph. So we only have to think about the increasing cases. But yeah.
So I didn't actually see the role of M. So where is M actually in this?
M. Yeah. So M is saying like how aggressively do we do Richardson iteration? How hard do we try to decrease the error? And so M, basically it's the power of E that we're using. And so that translates over here to how many copies of E do we tensor together?
That's the number of like M copies.
M, yeah, so M is like the number of copies of E that we tensor together.
So here's a question then. So L basically goes for, so M is supposedly much bigger than N, because otherwise I don't need to do anything.
No, it will be much smaller than N usually. Like if you want log, quasi-polynomial error, you just take log squares.
Yeah, M is very small.
So all the walks kind of like you eventually translate these two walks and you basically make these walks. So all of them are shorter than N. And they somehow all the relevant like walks which appear in these powers of e to the I actually are shorter than N. Is that?
Right. So each of these terms in the sum represents some kind of walk of length N, but it's divided up into like M components, and each component has length less than N. So each E individually is doing a walk of length less than N. And that's why we, that's why even though ultimately we only care about going from the first layer to the final layer, but somehow to make the analysis work, we have to be thinking about subprograms along the way. We have to be thinking about intermediate layers, going from layer I to layer J. And it's because of what you're saying. Each of these E's is thinking about going, well, what if we go from layer I0 to I1?
Yeah, another question. I mean, so we're trying to create like a weighted PRG, and I guess maybe something in the definition is the Laplacian, right? This is something that you get from the program itself, right? So this is isn't what you're getting here also like dependent on the program?
No, and so that's why I wanted to write this down so that I can show you that I have nothing hidden up my sleeve. This definition right here, this step 4 stuff, I wrote this down without reference to the program at all, right? GI to J is just based on Nissan's generator, and then this E thing is just based on the uniform distribution in Nissan's generator, and then this X thing we just sum. So none of this is specific to the program. Okay, so it really is a black box construction in the end. But then when you go to do the analysis, then we fix some program F, and we say, okay, what's the pseudo expectation of that program under this pseudo distribution? And what you get out, and this is something to verify, or you can read in the paper. We do explain it in pretty good detail in the paper. What you get out when you do that, that pseudo expectation calculation, all this analysis, all this matrix arithmetic is what happens. And what you get in the end is exactly the lower left block of this matrix. And that does depend on the specific program that we're trying to do.
Where is this sum of the X sub bits?
Good. Seed length. Okay, good. You're wondering about the seed length. Yeah, so far, this seed length is actually not what I promised. It's actually too large. Okay.
It seems like you multiply by.
Yeah, exactly. There's a multiplication. Yeah, so there's an issue.
One bit you pay twice. Pay with 1 bit to get rid of 1 bit.
Yeah, so the 1 bit here is not such a big deal. We can kind of ignore that. It's not a dominant factor here, but each of these terms, the E's or the G's, either one, this costs like S bits to sample from, where S is the seed length of Nissan's pseudorandom generator.
Yeah, but this is a space-bounded computation anyway, so you can fully use it.
Very good. That's step 5. Okay, so step 5 is that we decrease the seed length further. Okay, right now, if you think about, even ignoring the sum is something we have to pay for in terms of seed length too, but even ignoring the sum, this seed length is like S times M. Okay, but instead we wanted some kind of S plus, right? So the step 5 is that we replace, we approximately, we sample from something that looks like this distribution, but we replace independent seeds. This tensor product, this corresponds to like independent random variables. It corresponds to independent samples from Nissan's generator. Instead of using independent seeds, we'll use correlated seeds. And you can do this using a pseudorandom generator for space-bounded computation. Actually, Nissan's generator is not quite appropriate here because Nissan's generator doesn't have the best dependence on like the alphabet size. But you use a cousin of Nissan's generator, the INW generator. Okay. And this time, we need the error of this process to be very, very low. So this time the error is going to be, epsilon or like epsilon over 2 or something. But that's okay because now we're generating very few pseudorandom bits. Okay.
Can you use the same construction recursively with a weighted one?
It's a good question. So the only thing that you can potentially gain there is you could improve the log factors here, because we're always gonna be paying at least S bits this seed length of using of getting a moderate error. Okay, so we're definitely going to have to pay, if we're doing something like this approach, we're definitely going to have to pay this log W and log N. And we're also going to have to pay log 1 over epsilon somehow or another because that's simply optimal for any weighted pseudorandom generator or even hitting set generator. So if you're trying to do something clever and recursive, the best you could hope to do is get rid of these log factors. And we do actually know how to get rid of those log factors by a different approach. You do this last step slightly differently. So this time the error is very small, but that's okay because the number of pseudorandom bits we're generating is very, very small. Okay, it's only like pi logarithmic.
If you could improve Nissan for constant error, then this would just improve it.
Well, you would want to improve Nissan for inverse polynomial error, not constant error.
But isn't that because it's the L1?
Okay, but I'm very glad you're asking this question because this is sort of really what the heart of the new stuff is, which I'm finally going to tell you about some new stuff now. I hope that this was valuable. The new stuff is all about, wait a minute, can we do error reduction from a less, from a larger starting error? Okay.
I'm just not sure. So this is the error, the L1 error.
Yeah.
So is the L1 you mean expectation or sum?
So, okay, calculating the L1 norm of these matrices, in terms of branching programs, what that corresponds to is we consider a maximum overall start vertices, designate any vertex as the start vertex, and any vertex in layer I. And then you do a sum over all vertices in layer J of like, what's the error at that?
This is the operator now.
Right, this is the operator norm on these matrices. And so it corresponds to like total variation distance on the state space in layer J.
Okay, so you're using this one for polynomial error.
Yeah, inverse polynomial error.
And the new work is starting from bigger error.
That's right. New work is of all that starting from bigger error. Because now, okay, good. Okay, so what about regular programs? So for regular programs, I guess I shouldn't have erased everything that I erased. For regular programs, we would like to pull off the same sort of strategy. So for regular narrow, and we're thinking about narrow programs like constant width.
You want to take a break before we start the regular?
Oh, sure. Yeah,
Take a 5-minute break.
sure. Yeah, let's do a 5-minute break. Sounds good.
So let me ask you, so the Richardson method should work like for arbitrary M, is that right? Or like I could like really huge M. But this would actually wouldn't go through because or would it actually? No.
You can take M, you can take M extremely large. And that's exactly what we do if you're shooting for a weighted pseudorandom generator where epsilon, if you're demanding of an extremely small error epsilon, then that's exactly what happens. We take M extremely large, and that's perfectly legal and it all works out.
But then, like, what's going to be the length of these? This is going to give you. This is giving you some pseudo distribution on strings, but the length of the strings will be depends on the M. So if you take a huge M, then it's kind of going to be.
So the M does not affect the length of like the strings that the pseudo distribution is over. Instead, it just affects like the number of parts that it's broken into.
M will be empty. That's what you're saying.
Yeah, if you're taking M like even larger than N. Yeah, if you're taking M even larger than N, then like a bunch of these correspond to a bunch of. But M,
it's basically going to be just uniforms. Like
M should not be quite that large. Then everything does kind of get degenerate. Yeah, that's kind of the limit. Yeah. So, all right. So now we'd like to talk about regular programs, and we'd like to pull off something similar. We want to do error reduction for regular programs so we can construct a low error weighted pseudorandom generator. Okay, so step 1 prime is very similar to step 1. But now, instead of using Nissan's pseudorandom generator, we'll use the state-of-the-art pseudorandom generator for narrow, regular Riemann branching programs, which is this generator that I mentioned earlier due to Braverman, Rao, Raz, and Yehudayoff. There we go. So we use the BRRY pseudorandom generator to construct these W tilde matrices. Okay, and this time it's going to be most convenient to think about the infinity norm. So we're just swapping, now we're considering like a worst case target vertex, and then we're summing over all start vertices. But okay, and this is going to be at most some moderate error tau, but this time we cannot afford to take tau so small. Okay, we cannot afford to start with an inverse polynomial error. Instead, we're going to start with the initial error is 2 to the minus square root log n. Okay, the reason is because of the seed length. The seed length of this BRRY pseudorandom generator is log W over tau times log n. Okay, we're thinking of W as a constant. So this is log to the 3/2 n. We can't afford to take tau to be this inverse polynomial anymore. If we took tau to be so small, then just the seed length from this moderate error pseudorandom generator would already be log squared n, and our goal is to beat log squared n.
So we are talking about constant width,
Constant width, yeah.
not regular. Regular was not the regular result is not with bounded.
So the regular result, it applies to any width, but it's most interesting when the width is small. And let's say W is a constant for the sake of simplicity. Yeah, because the seed length that we're aiming for, it does have a log W times log n term. Okay, so if the width is large, like polynomial, then it's not interesting. We're just recovering Nissan's result. So think of W as a constant, but it doesn't have to be 3. Okay, it could be 100. All right, get it. Okay, so tau is larger, which means we need to change something else in this construction because of this crucial factor of n blow up, right? If we just do everything the same way from here on out, then we won't get anything because this factor of n blow up will completely swamp this moderate error tau. So we need to do something different, and the main difference is in how we do step 2. This construction of L hat inverse. Okay, this way that we collect all of the W tilde matrices together into one big matrix. So instead of just arranging all the W tildes in this L hat inverse matrix, instead we're going to put like some products of some W tildes. Okay, and the specific choice that we'll make is based on this thing that's called a shortcut graph. Okay. So the shortcut graph, it's a graph on the, let's give it a name. SC sub n. It's a graph on the integers 0, 1, 2 up to n. Okay. Actually, I want to draw more than that. And the definition is that we include arrows from each number to the next. And then we also include these shortcut arrows of length 2 going from each even number to the next even number. Okay. And we also include more shortcut arrows of length 4 going from each multiple of 4 to the next multiple of 4. Okay, and etc. for each power of 2. Okay, so now what are we going to put in a particular block of our new matrix L hat like let's say the IJ block, or let's say the LR block actually. Okay.
Will be a matrix of the same size.
It's going to be a matrix of the same size. That's right. It's still going to be this big matrix, capital N by capital N, where capital N is the number of vertices in the branching program. So, and I just need to tell you, like, what are going to be the blocks? Each block is a W by W matrix. Okay. So let's let L and R be the block that we're looking at. Okay. Then L and R are numbers here in this graph. We're going to look at the shortest path from L to R. Okay. So let's let I0, I1, IK be the shortest path in the shortcut graph.
You have the W's in this interval, the product of the.
Yeah, that's right. That's right. So we're going to let the R from L block of this matrix L hat inverse be the product. W tilde IK from I product, and then W tilde I1 from I0. Okay, and this is maybe I should have written step 2 prime earlier, but yeah, step 2 prime is that our new matrix L hat inverse, our new definition is that we collect all of these, collect all of these blocks. So we have we still have the identity on the diagonal, 0 above the diagonal, but now we have these blocks, L hat inverse. So I think this is a kind of a bizarro definition. It's maybe not clear looking at it what benefit we're gaining. Maybe I should say this is inspired by a non-black box algorithm by Ahmadinejad, Kellner, Murtaugh, Peeble, Sidford, and Badon. And in their algorithm, this corresponds to some kind of recursive Schur complement thing. And that's not something that I understand very well. And that's part of why, we were interested in this whole subject, is we wanted to understand this better. But this somehow this like corresponds to this recursive Schur complement, if that means anything to you. But the point is that this construction kind of magically enables us to avoid paying this factor of n here.
By logn.
I'll write down a theorem that says exactly what it's replaced by, but yeah.
Very strange, because now the powers of this L inverse don't look like it's like in the previous structure you have if you took just first lower diagonal, when you square this matrix you get the next diagonal and so on. Here it doesn't seem to correspond to.
Right, so it's a little wonkier, right? But it does still at least satisfy some sort of basic sanity check things, right? Each entry of this matrix at least seems to be an approximation of the corresponding block of the true inverse Laplacian, right? If we're multiplying these things together, if we multiply a few of these things together, that should be an approximation, to going from I0 to IK, right? And the fact that we're multiplying in terms of our seed length, that we have to pay for that because multiplying corresponds to taking independent seeds to the BROY generator. But this graph here, the shortest paths are not that long; they're only logarithmic, so the penalty is not significant. Ultimately, it has no asymptotic effect. But yeah, you're right. I think it's a little less intuitive. It's not the natural thing to do. Okay, but the theorem is. And this is the theorem that uses regularity. So if f is a W regular program. Then with this definition, we have the identity minus L hat inverse L. Instead of tau times n, it's tau times W cubed times log n, exactly as you said. And as a result, we can afford to start with this larger value for tau. Okay, so if we can take this theorem as given just for a moment, then steps 3 prime, 4 prime, and 5 prime are basically the same as before. Okay, so we maybe fiddle with the parameters slightly, but it's the same as before because everything else still makes perfect sense. It's really just that factor of n blow up that we needed to, where we needed to solve something.
So what's the implication with the regular, basically in the regular programs, you don't use that for PRG. The distribution never loses that, right?
Yeah, so yeah, that's true, and that's relevant. The intuition here comes from this work by this BRRY work, right? So basically, the idea is that like there can only be a limited number of steps that really matter in this computation in a regular program. In a regular program, for many of the steps, most of the steps even, it kind of doesn't matter which vertex you go to. You're going to have essentially the same acceptance probability either way. Okay, and this is showing how to somehow take advantage of that property of regular programs, in this context.
Because entropy cannot increase too much, too many steps. Or so the distribution cannot change.
Yeah, so it's potentially helpful to think about like the reversed random walk in this regular program. Okay, really the best way of thinking is in terms of this like weight quantity that was used in the pseudorandom generator analysis. So okay, hopefully we'll get there though. So let's.
But it really is sensible only if the weight is very small.
Right. Yeah, this business about the weight is, yeah. It turns out though
You're also losing you're losing for large weights you won't get anything.
Right. Yeah, but I should say this construction makes sense potentially in other settings as well. Okay, so in the paper actually we also consider some other models. We consider unbounded width permutation branching programs, and we consider polynomial width regular programs in the non-black box setting. And for those cases, actually, this construction still makes sense, but then you have to use a more sophisticated matrix norm. Here we're thinking about the infinity norm. You have to use some a more complicated matrix norm that's harder to interpret. But the construction actually still makes sense. So much of this is like a pretty general framework. And as you'll see, the first several steps of the proof of this theorem don't use regularity. But then at some point, we are crucially going to use regularity, and we'll pay this factor of W.
Does it make sense to consider other graphs rather than the shortcut one?
Yeah. I don't know what could be gained, but maybe something, right? We're using certain properties of this shortcut graph, like things like these edges, they don't cross each other, and that actually kind of plays a role. But yeah, I mean, potentially. I mean, I don't know.
Where does the blow up in W come from in this method?
Yeah, so it has to do with what Avi was talking about here with this, the weight of this. Yeah, it has to do with these weights. Like this claim I was making that many of the steps don't matter. That's only true if you're considering narrow regular branching programs. And I think hopefully we'll get to see quantitatively where that shows up. Okay. Okay, so let's start proving the theorem. Or at least sketching. Okay, so we're trying to argue that L hat inverse is a good approximation to L. So in that, for that reason, let's try to express L hat inverse in terms of L. Okay, or in terms of L inverse, rather. Sorry. Yeah. So in order to do that, we need to like sort of write down like what are the errors. So let's let ij be a shortcut edge. So it's an edge in this shortcut graph where j is bigger than I plus 1. Okay. Let m be the midpoint. So m is I plus j over 2. And let's let delta w j from I be capturing the error between, if you take this shortcut edge or if you don't. Okay, and what I mean by that is if you go straight from I to j, how does that relate to taking a pit stop at m? Well, how it relates is according to this delta.
Comparing the new L tilde to L inverse.
Not yet.
Rather to the previous.
Right. So far, yeah. So you were comparing this, W tilde to itself. It's in the same spirit as this notion of local consistency, perhaps. But we're going to use this in order to compare L hat inverse to L inverse. Yeah. Okay, so now we have this this formula for W tilde j from I in terms of like shorter edges in the graph. Let's substitute that into here. Right here we have this formula for a block of L hat inverse, and it's in terms of these W tildes. Okay, so by substituting that in, we're going to be replacing long edges with short edges. Okay, and we'll do that recursively. Just keep doing it over and over again to shorten all the edges. Okay, until we're down to length 1 edges. So
All right, omega times stupid coming from. But it seems like omega you lose from the L infinity.
I see what you're saying. Yeah, you're saying you should expect to pay this log n.
You should expect to pay log n because you are iterating it log time, but I see only omega because you are just summing over all the vertices in a layer as you have an L infinity bound. So I don't know why it's omega cubed that time.
The W, the width.
Yeah.
W, yeah, I guess my handwriting. Yeah, and maybe W, maybe you shouldn't have to pay W cubed, maybe W squared or something is more, right? But I'm not 100% sure that the W. Okay, good. So, okay, we recursively substitute this thing into there until, into the formula for one block of L hat inverse until we're left with, there are two types of terms that you're left with. They're the edges of length 1. Okay, and for convenience, we're actually going to assume that on edges of length 1, the approximation is perfect. Okay, this is like without loss of generality. You can modify the pseudorandom generator if you'd like. This BRRY pseudorandom generator that we use to construct them. You can modify it so that the first output bit is perfectly uniform random, so all that these length 1 approximations are perfect. And then we also have these delta terms floating around. And and here J is bigger than I plus 1. Okay, so let's like unify these two terms. Let's let W hat J sub J from I be, you know, whichever of these is applicable. All right, W from J to I if J equals I plus 1, and it's delta W J from I if it's a shortcut edge. And 0 otherwise. So after we do this recursive substitution, after we keep putting this into that formula over and over, eventually we're left with a bunch of these W hat terms. Okay, and if you work it out, here's, you know, a place where you'll have to trust me a little bit. And this is where we're using certain basic properties of that shortcut graph. But what you end up with is this formula for L hat inverse, which is the sum over all paths. Okay, so the sum from t equals 0 to, you know, this is the length of the path, and then the sum from sum over all paths of length t from L to R. I0, I1, IT. And then we do the product of these W hat matrices now. Okay. Okay, so you know, why are we making progress here? How is this helpful at all? Well, if we're summing over all paths and then multiplying along that path, right? That almost sounds like the inverse of a Laplacian matrix. Okay, an inverse of a Laplacian matrix tells you, you know, what are the probabilities of going from any vertex to any other vertex by any path you might take through this program. Okay. And so indeed, you know, this is L hat inverse is exactly the inverse of I minus W hat. Okay. Where W hat is like the collection of all these, you know, these W hat matrices that we considered. Okay. W hat. W hat. Okay, and this is why we use this notation L hat inverse, which maybe seemed a little awkward at first because I was saying it's the approximation to L inverse. So maybe it seemed like it should have been like L inverse and then a hat over everything. But actually we're using this L hat inverse because it's actually the inverse of something. L hat actually matters to us. Okay, so this is the inverse of L hat. Okay, so this is why the title of this paper, if you remember at the very beginning, it had this strange phrase, inverse analysis of random walks. It's because this step right here, this is like we're taking, okay, we have this matrix that we constructed, this L hat inverse. Here it is. And look, yes, I admit this is not exactly equal to L inverse, right? This is, I'm only trying to claim it's an approximation. But this is the exact description of random walks in some other graph. Okay, this is the exact inverse of some other Laplacian. And looking at that other Laplacian turns out to be helpful to us. Okay, so it's like we're starting with the description of all the random walks, and then we're trying to reconstruct some graph, and that's what's described by this W hat. Reconstruct some graph that's consistent with that description. Reconstruct some graph so that random walks through that graph. Okay, and admittedly, this W hat graph, it's not like strictly speaking a read once branching program anymore because it has these shortcut possibilities. You can skip forward. And also admittedly, okay, technically these aren't random walks anymore when we look at the inverse of this Laplacian. now they're like weighted walks because this W hat involves like some negative numbers. Okay, it involves these deltas, these, the delta is a difference between things. So, okay, these are like weighted walks through this graph, but morally, this is like we're running the process of analyzing random walks in the reverse direction. Yeah. Okay, but what does this buy us, right? Okay, so our goal is to bound this quantity identity minus L hat inverse L. It's basically equivalent. You can verify this. It's basically equivalent to instead take the inverse of everything and bound the identity minus L inverse L hat. Okay, so then what is this? This L inverse L hat. This L inverse L hat matrix, this is saying, you take some random walk first through this W hat matrix, and then you take the remainder of your walk is through this the correct the perfect random walk through the original branching program. Okay, so with this L inverse, doing the actual L inverse, now we can write this as L inverse times L minus L hat. Which is L inverse times this delta W thing. Okay, because W hat here is W plus delta W. Okay, now it's helpful to decompose this delta thing. So this delta, remember delta is talking about like the difference between edges of one length versus edges of half the length. And it's helpful to decompose it into, based on which lengths we're considering. So we'll decompose it as a sum from I equals, or I think I used a different letter rather than I. So T equals 1 to log n of delta W T, where delta WT only handles edges of length 2 to the T.
That's the W is something like minus 12 again.
Right. We're going to show the L inverse times delta W T, one of these individually, the norm, the infinity norm still is like W cubed times tau. Okay, and the log n right here comes from summing over all T's. Okay, so now we're comparing, as you were saying earlier, we're comparing like the W tildes to themselves, right? We're comparing W tildes of one length versus W tildes of half the length.
The analysis of Nissan generator from the beginning, right? I mean, you will just double.
Absolutely. Right.
Comparing two independent seats to one.
Absolutely. Right. The only thing that's potentially tricky here, and the reason we're going to need regularity, is because if we're going to use the infinity norm, and I'm telling you that turns out to be a good choice, then we're considering a worst case target vertex, and then we're summing over all possible start vertices anywhere in the program, and yet we do not want to pay a factor of n. Yeah, so far, all of this, all of this, none of this has used regularity, right? And all of this is still a good idea, even in other contexts. Going forward, we're going to start doing stuff that really only makes sense in the case of these like regular bounded width branching programs. So let's look at a single entry of this matrix whose norm we're trying to bound. Okay. We'll look at one entry, then just working through the definitions, the like VU entry is like we were saying, it's comparing, W tilde of one length versus W tilde of half the length, but then also we'd have this true random walk through the original branching program that happens after that, right? So it comes out to, we do some true random walk from, let's say, layer R to layer K, and then we have 2 copies of the pseudorandom walk versus the same true random walk but now we do 2 independent pseudorandom walks, with this midpoint M along the way. And then look at the, corresponding entry of that. So U is in layer L and V is in layer K. Okay, and R here is L plus 2 to the T. So R is like how many steps of the pseudorandom walk do we do? So we're comparing these 2 things to each other. The approach is that we'll show that each of them is close to the truth. Each of them is close to the true probability of going from U to V if you took a true random walk through the original branching program. Okay, and the proof of this uses these techniques that were introduced by Braverman, Rao, Raz, and Yehudayoff in terms of the weight of the branching program. Okay, so I'll quickly review some of that, but I won't do it in full detail. This definition is that the weight of an edge in the branching program is the difference in acceptance probabilities from one endpoint versus the other. So the acceptance probability, if you start at U, versus the acceptance probability, I was using F, versus the acceptance probability if you start at V. Good. Now, in this situation that we're analyzing, where you do first you read some pseudorandom bits and then you read some truly random bits, the error of that situation is basically governed by the weight of this portion of the branching program, the weight of the portion where it's reading pseudorandom bits. Okay, we're asking like, how much does it matter that you didn't arrive at quite the right vertex after reading those pseudorandom bits? Okay, so concretely we can say suppose X fools, these width W regular programs. X is a distribution. Yeah, X is a distribution and it fools these regular programs with this moderately small error tau. Then if we read X followed by uniform random bits, then it fools some regular program F with error that's like tau, and might be much smaller than tau actually. So it's tau times the weight, and then, okay, there's some little factor of W that you maybe don't necessarily need here if you set up your definitions right, where W is the weight of the, like the total weight of all the edges in the first capital X many layers. Okay, I guess when I'm saying first, I'm kind of assuming here that L is the first layer for simplicity. Okay, so if the weight of these first few layers is very small, if those first few layers, basically don't matter to the computation, then that works in our favor. And actually, the error that we pay here is actually smaller than tau. We don't have to pay the full error of the pseudorandom generator, basically because it kind of doesn't matter what the pseudorandom generator did. It didn't matter which vertex we arrived at if the weight is much smaller than 1. Okay, so I won't prove this lemma, but I hope it's intuitive.
So W can be 0.
Yeah, could be 0, could be 0. But the case to think about for this lemma, I think, is that W is some very small number, smaller than 1, bigger than 0.
Zero, this just means that it doesn't matter at all what you've done in the first bit. So you
Yeah.
like, what do you care about if it was pseudorandom or not? You just
Exactly.
start from
All the vertices in that middle layer have exactly the same acceptance probability. So regardless of which one you arrive at, you're going to have exactly the right acceptance probability. Yeah, that's right. Good, 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 good. Okay. So consequently, what we get here is that if we look at one of these two things, I mean, they're basically the same, but let's focus on this one, right? Then let's look at, we're still just thinking about one entry though. K from R, and then W tilde R from L versus the truth. You get this tau times some little factor of W that maybe doesn't matter, and then times the weight of our program if you only look at edges in the layers from R to L. Good. And that was just one entry, but now when we look at the infinity norm, we're going to be summing over the entire length of the program, right? We're summing over, most importantly, we're summing over all L. Okay, we're considering a worst case target vertex V. So the infinity norm here, if we think about we have its worst case for the target vertex V. Actually, this should be like the weight when you're thinking of V as the target vertex. Okay, so we have this worst case over a target vertex, and then we sum over all starting vertices. So effectively, we're summing over all L. And then there's another factor of W because of we're considering all vertices in that layer L, but it's like tau times W squared. So now we're summing the weights of all the different portions of this branching program, which means we're getting the total weight of the branching program as a whole. Okay, And then, I won't show you this proof either, but in Braverman, Raz, and Yehudayoff's work, when they introduced this concept of weight, they showed that a regular program has a weight that's bounded by its width. Okay, in a constant width regular program, the total weight of all these edges is bounded. Okay, there can only be a few steps that actually, really significantly matter for this computation.
This is regularity.
Yeah, this is really the key step where we're using regularity, is to bound the weight.
Some of it must be related to the effects that entropy can only increase and can reach W in a regular program that you don't go up and down, and there's some monotonicity in the error accumulation that.
Yes. Yeah, I think it is closely related. Yeah, so I mean, if this proof that like the weight is at most the width of the program, it's proven by like a kind of a potential argument that can be phrased in terms of these entropies, but it's in terms of like the entropies in the reverse direction, which is maybe a little counterintuitive. But you argue that like you sort of argue that in each layer, like one of two things happens. Like either there's no significant weight in that layer, or if there is significant weight in that layer, then that must mean that the reversed walk gained a significant amount of entropy. But that can, there's only so much entropy that you can gain. Eventually, it's uniform. Yeah. So so you're totally right. Okay, great. So I mean that's the end of the proof, right? If you trust this claim about bounded weight, there are a couple of points where you had to trust me, but if you trust me about those points, then at this point I've shown you that this I minus L hat inverse L, it's only like tau times log n instead of tau times n, at least if we have the programs of bounded weight. Okay, so before I spend just a couple of minutes telling you about width 3 programs, is there any, does anybody want to stop me with questions about the case of bounded weight regular programs?
So from here you proceed with the same Richardson and the same simulating Richardson with this weighted pseudorandom.
That's right. From here, everything is basically the same. Okay, you do have to be, you have to make sure that you can still reverse engineer this construction because it's a slightly different construction. But you can. It's just there are slightly more tensor products in that description because we have this. We multiply together a few copies of these W tilde matrices, and that means we pick up another factor of log n in terms of the number of E pseudo distributions that are getting tensored together.
Why do you start? Why did you pick 2 to the minus quote again? Why didn't you pick constant?
Right. It's to balance two things. So in the end, we have this. We have to pick M, which is like how aggressively do we do error reduction? M is roughly. Okay, I shouldn't say it until the and the roughly. M is roughly log 1 over epsilon over log tau. Log 1 over tau, I mean. And the seed length involves a plus m log n term, yeah. Sorry, I got confused, but yeah, the seed length involves a plus m log n term. So we don't want to take m to be too large, but we also don't want to take tau to be too small. And because it involves also this BRRY seed length that has a log n times log 1 over tau. And so if we take tau to be very small, then we'll pay from the BRRY seed length, and if we take tau to be very large, then we'll pay for this error reduction seed length. So the 2 to the minus square root log n balances these two terms. This is from Richardson iteration, and this is from our base pseudorandom generator. Okay, good. Okay, so I'll just very briefly say something about width 3 programs, because we spent a lot of time here. So for width 3 programs, it actually builds on this weighted pseudorandom generator, which is why I wanted to show you this one. So it's based on these ideas by Meka, Reingold, and Tal, where they designed an unweighted pseudorandom generator for width 3 branching programs. And their approach was they do a bunch of pseudorandom restrictions, and they argue that after applying a few pseudorandom restrictions, with high probability, their width 3 program almost, in some sense, becomes a permutation program. Okay, which is even stronger than saying that it almost becomes a regular program.
How many bits are left unfixed in this?
Yeah, like n over polylog n many
Are left?
are left still alive. So the restrictions are pretty mild. Okay, the restrictions, you just assign half the bits at a time, and you do that maybe log n many times. So you're still leaving quite a lot of bits alive, and yet quite a bit of simplification occurs. Okay, so they argue that it becomes almost, in some sense, a permutation program, and so then they can apply the INW generator using analysis building on this Braverman, Rao, Raz, Yehudayoff work to try to fool this almost permutation program. Okay, our approach is that we do the same kind of thing, except as a final step, instead of using the INW generator, we use our weighted pseudorandom generator that fools regular branching programs. So I think it's a simple idea. Unfortunately, it's kind of non-trivial to make it work. But one of the fortunate things of this is that in the process of making this work, we were able to prove a much cleaner version of this statement, actually. Okay, so a much more, here I'm not even going to write down what it means. In their work, what it meant for it to almost become a permutation program was a bit complicated. But in our work, we can actually say something rather clean. And so I'll tell you, what that statement is, and then I'll stop right there. So I'll just write down one theorem here. The theorem is there exists an explicit distribution over restrictions such that first of all, we preserve the expectation of any width 3 branching program. For any width 3 F, we have, if you do this random restriction and then you plug in uniform random bits to the restricted function, then that's close to the expectation of F. So we're not doing any harm when we do these restrictions. Okay. And second of all, we're gaining something. Okay.
The seed length for the restriction is just logarithmic.
Yeah, and I'll write that down as the last thing, but that's right, the seed length is near optimal. Okay, so with probability at least 1 minus epsilon, this program F becomes permutation-like or regular-like, and specifically what we can say is that it has low weight in this exact same sense as Braverman, Rao, Raz, and Yehudayoff. Okay, so the weight of the restricted program is at most polylog n over epsilon. And then finally, as Avi said, this restriction is low cost. Rho can be sampled using log n over epsilon truly random bits. Okay, so we were able to prove this using, by building on the ideas that Meka, Reingold, and Tal used. It's the same kind of intuition behind our proof, but it's, I think, a much cleaner statement. And more importantly, it's a statement that's compatible with our analysis of regular branching programs over here. It's in terms of the weight. Okay, and so these two things fit together, and that's how we get our weighted pseudorandom generator for width 3 read-once branching programs. Okay, so I'll stop there. Thanks for listening. Sorry for going a little over time, and I'm happy to take more questions.
I think for width 3 to get anything optimal, you need completely new ideas or
That's a good question.
more.
Right, so you're saying, I mean, we have this still like square root log 1 over epsilon. We have, you know, if the error is 1 over n, then we're getting a seed length of log to the 3 halves then. And you're wondering, can we get down to a seed length of log n over
To
epsilon?
get the best.
Yeah, it's a good question. I don't know. I mean, so the challenge I would say is that all of our error reduction techniques that we know always have this same phenomenon where m is like log 1 over epsilon over log 1 over tau, something roughly like that, or in some cases worse, but this is like the best we can hope for with these if we're using these error reduction methods. And then we always have this m log n. Okay, so it seems really hard to avoid this trade-off that's happening right here for width 3 programs if we're going to use this kind of error reduction approach. Okay. But that being said, I mean, you don't necessarily have to be using all this error reduction stuff for width 3 programs, right? You could be, for example, you could be aiming for a true pseudorandom generator. I think that's perfectly reasonable to try to do. And if that's your goal, I encourage you, but I would encourage you to first think about the following case that seems almost silly because it's such a special case, but we don't know how to handle it. The case is width 3 permutation read-once branching programs. Okay, this is a pretty weak model. I mean, you can kind of get a pretty good understanding of like exactly what these programs are capable of. They're, you know, in some sense, they cannot be all that complicated. And yet, even for that specific case, we don't know how to fool it with low error with a seed length better than Nissan's generator. If you want to, you know, a true pseudorandom generator with optimal seed length, we don't know. And that's kind of like, that's the important bottleneck. I mean, as you can see, in the general case, we're trying to reduce to something that's permutation-ish. So I think that's the natural case to think about. And yeah, I don't know how to do it.
Okay, thanks.